Okay, so welcome to this next video in the playlist on vector spaces. In this video, what we're going to actually see is what the definition of a vector space actually is. Okay, so let's begin with that. So a vector space is going to be another type of number system. So we've seen that a group is a type of number system, okay, that obeys a bunch of axioms. We've seen that a field is a type of number system which obeys a bunch of axioms. Now what we're about to see is that a vector space is also a number system, a type of number system that obeys a bunch of axioms. Okay, so that's what we're doing. Once again, we are defining a type of number system, and any number system that you have which obeys all of these axioms that I'm about to list off will be considered a vector space number system. Okay, right. So first thing to say is that when you're defining a vector space, you need to have a field, okay, in mind that you're working with. Okay, so you can't define a vector space without having some field in which you are going to have the vector space being over, which is why it was necessary to firstly look at the definition of a field before we could look at the definition of a vector space. Okay, so what we're going to have is a vector space which we'll call capital V, but it's going to be over a certain field, and this field can be an abstract field, so I'll just call it capital F. Okay, so you need to have some field that you're working with. Okay, now what we're going to do is define what is meant by a vector space capital V over that field capital F. Okay, so this vector space then, capital V, as always with these number systems with groups and fields, what it's going to start off with is just being a set of symbols. Okay, so it's going to start off its life as just a set of symbols, and you can make this set of symbols up. Okay, so this could be a finite set of symbols or it could be an infinite set of symbols. Okay, so here is the starting point for our vector space. We've created a set of symbols. Okay, now what we're going to do, to turn it into a vector space over the field F, we need to have two composition laws on this set of symbols. Okay, now the first one is a nice simple one, and the second one is something new that we've never seen before. Okay, so the first composition law on this set of symbols that is our vector space is called addition. Okay, so we need this first composition law which is called addition here. Okay, and I'll colour addition in green. So we'll have our composition table of addition here in green, and again the symbol for this composition is just the plus symbol, as usual. Okay, right, so what you'll do is you'll put all the elements of the set that is the vector space V over here, and I should just say that the elements of a vector space are called, you might be able to guess this, they're called vectors. Okay, so the elements of a vector space are going to be called vectors. The symbols in this vector space are going to be called vectors. Okay, so what you're going to do is you're going to put every single vector in the vector space down here in our addition composition table here. So we're going to give every single vector in this set a row that is dedicated just to it, and you're also going to give them all the columns. So up here in the titles of all the columns in this addition composition table, again you'll put all of the vectors in the vector space. So I'll just colour these in here. So you'll put all of the vectors along there, and then what you'll have to go through and do is define what any two vectors added together is going to be equal to. Okay, and the answers there will of course be other vectors from the vector space capital V from this set here. Okay, now this composition law of addition, it has to obey a bunch of axioms, and it has to obey the axioms of an abelian group. Okay, so we've been through what an abelian group is in the video on the definition of a field. We've also been through it hugely in the playlist on group theory, so I won't at this point remind you of the axioms of an abelian group. Okay, we will actually see them later on when we go on to actually discuss some examples of vector spaces, but for now I'll just let that go down without further explanation. Okay, so this composition table needs to obey the axioms of an abelian group. So with just this composition of addition on it, this set of symbols should be an abelian group. Okay, however, to turn this abelian group into an actual vector space over the field capital F, we need another composition defined on top of this. Okay, and this other composition is where the field capital F is going to become important. Okay, so this second composition table over here is going to be called scalar multiplication. Okay, and this is not a composition table of elements of the vector space with elements of the vector space, unlike addition and unlike all of the composition tables that we have seen before. Instead, it is a composition table involving elements of the field capital F here and elements of the vector space capital V. Okay, so let me draw a picture of this. So here is going to be our scalar multiplication composition table, and of course the symbol for this will just be a time symbol. Okay, and what we're going to now do is we're going to give all of the elements of this field, capital F here, this number system that's a field over here, we're going to give all of the elements of that number system rows in the composition table. So down here, what we'll do is give all of the elements of this field rows in our scalar multiplication composition table. So all of the elements of the field are going to appear down here. Meanwhile, up in the titles for the columns, we're going to put all of the vectors of the vector space. So we'll put all of the vectors of the vector space up here, and I'll denote that in vivid purple here. So we put all of the vectors here, and we're going to now define a composition law which is going to involve composing or multiplying any element of the field by any vector from the vector space. Okay, and all of the answers that we get here are going to be back within the vector space. Okay, now this scalar multiplication table is going to have to obey a bunch of axioms, and if it does obey those axioms, then overall this vector space that we have here will actually be a vector space over the field F. So I hope you understand why when defining a vector space you need to have a certain field in mind. Okay, you can't obviously do this if you don't have a field. Okay, so you have to have a field. A vector space is defined over a field. Okay, right, so let's now say what axioms then does this scalar multiplication table need to obey in order for this to actually be called a vector space. Okay, so axiom number 1 I've already actually stated, that's closure. Okay, so that means that if you take any element of the field, so for all little c is an element of the field capital F, and if you take any vector, so all little v, which is an element of our vector space capital V, it must be the case that if I multiply c by v in my scalar multiplication table, and often when we write an element of the field multiplied by an element of the vector space, we don't actually put the multiplication symbol in there. Instead we just put the element of the field next to the element from the vector space, similar to as we would in a field where we don't usually write out the actual multiplication symbol. Okay, so this must always be an element from the vector space capital V again. Okay, so drawing that on the picture here, that means that if we take any element of the field, little c, so what we'll do is take the row here corresponding to this element of the field, little c here, and we take any element of the vector space, little v, so what we'll do is take the column dedicated to little v here, and we look at the answer in the scalar multiplication composition table, which is c times v. This must be some other vector from the vector space capital V. Whatever it is not something that is outside of capital V. It is within capital V. So that means that all of the entries in the scalar multiplication table have to be back within the vector space capital V. So we need scalar multiplication to be closed. It needs to always give elements from the vector space capital V. Okay, so that's the first axiom then that scalar multiplication must obey. Now let's go over axiom number 2. Let's see the second axiom, which is a little less easy to understand. Okay, so axiom number 2 is associativity. Okay, so it concerns it taking two elements of the field this time. So we'll say we have C1 and C2, which are both elements of the field. Okay, and then we'll have one element of the vector space, and for all little v is an element of the vector space. If we consider what is C1 multiplied by c2 times v, like so. And make sure you understand what this actually means. This means firstly take the vector v and scalar multiply it by c2. The answer that you'll get there, c2 times v, will be another vector, okay, by axiom number 1 of scalar multiplication. Okay, and then what you're going to do is take that other vector and then multiply that by the second element of the field, c1. Okay, and the overall answer that you then get is what I mean by c1 times c2 times v in this way. Okay, right, so axiom number 2 is going to say that this must be the same as if we firstly compose under multiplication c1 and c2 together and then scalar multiply that by the vector v. Okay, so on this side, on the right hand side here, what this means is we are firstly multiplying c1 and c2 together in the field. Okay, so the field has a multiplication law defined on it. You can multiply these two elements of the field together in the field. Okay, so you'll multiply c1 and c2 together in the field and then take whatever answer, which will be another element of the field, so whatever this is, it will be an element of the field, capital F, and use that to then scalar multiply the element v. Okay, and what this axiom number 2 says is that both of those ways of doing things must give the exact same answer, basically. Okay, and the way we would what we would call this property is we'd say that it's associativity. We say that scalar multiplication must associate with multiplication in the field. Okay, right, or must be associative with multiplication in the field. Okay, so that's axiom number 2 then, and I'll just put the title, so I'll give these axioms names. So this is associativity here, okay, and this first axiom over here was closure. Okay, so now let's move on to the third axiom then that this scalar multiplication composition table must obey. So axiom number 3 here. Okay, so axiom number 3 concerns the multiplicative identity of the field. Okay, so I'll put this on my picture. So the field will have a multiplicative identity which will be denoted 1. Okay, and we now want to consider what this multiplicative identity multiplied by any element of the vector space is actually going to be equal to. Okay, so we want to consider what is 1 times v, and basically axiom number 3 says that the multiplicative identity of the field must multiply by any vector to give that vector back again. So basically, if we look at the row dedicated to the element 1 in the scalar multiplication composition table, it will contain all of the vectors in the vector space capital V, okay, and they will appear in the exact same order as they do up here. So to look at, this row will look like a replica of this portion up here, which is the title row, which gives the title of all of the columns here. Okay, right, so axiom number 3 says that whatever little v you pick from the vector space capital V, the multiplicative identity in the field 1, scalar multiplied by that vector, must give the vector back again. Okay, so that's axiom number 3 then, that the scalar multiplication must obey. Okay, and now what we want to go on to is axiom number 4 then. Okay, and axiom number 4 has 2 parts. Axiom number 4 then is distributivity, but there are 2 distributive laws that need to hold. Okay, so I'll give you the first distributive law, and then I'll give you the second one. Okay, so the first one concerns if we take one element of the field, so for all little c is an element of the field, and we take 2 elements of the vector space, so let's say v and v bar. Okay, so we've got 2 elements of the vector space. Okay, so what now happens if we add v with v bar with our addition composition law that we've got defined on the vector space? So we can add these 2 vectors together, and then we can take the answer and scalar multiply it by c. Okay, what do you think this is going to be equal to? Well, the answer is that we're going to insist that it should actually equal the intuitive thing, which is c times v plus c times v bar. Okay, so we're going to insist that it doesn't matter whether you first add the two vectors together and then take the answer and scalar multiply it by c, or if you firstly scalar multiply each of these two vectors by c and then add them together. Okay, so this basically is that scalar multiplication should distribute over the addition in the vector space. Okay, and that should be true for whatever little c you pick and whatever v and v bar you pick. Okay, so that's distributivity number 1, but there is actually a second distributivity that we're also going to insist on, and this concerns what if we have two elements of the field. So for all C1 and let's say C2 that we can pick from the field, capital F, and this time we'll just have one vector, and for all little v is an element of the vector space, capital V. Okay, now let's consider what happens if we firstly add together these two elements in the field. So we're going to add C1 to C2 in the field, okay, and then we're going to multiply this by V. Okay, well again this is going to equal the intuitive thing, which is C1 times V plus C2 times V. Okay, so what we're going to do is on this side we firstly add C1 and C2 together in the field and then take the answer and multiply that by the vector v through scalar multiplication. On this side what we do is we firstly scalar multiply C1 with v and C2 with v, and then we add them together in the vector space. So this is quite complicated here because this addition is in the field, this addition is in the vector space. All the multiplications that we have here are indeed in the scalar multiplication. Okay, so this basically is saying that addition in the field, that scalar multiplication should distribute over addition in the field as well as just addition in the vector space. Okay, so that's part 2 of distributivity. Now, part 2 of distributivity instantly tells us something about what multiplication by the additive identity of the field with any vector through the scalar multiplication composition table should do. Okay, but before I actually look at that, let me just go back to the addition composition table over here. Okay, so I said right at the start that my vector space would have this addition composition law on it, and this addition composition law would obey the axioms of an abelian group. Now that means that it has an identity element, some vector, which when it adds to any other vector gives that other vector back again. Okay, we will call this vector the 0 vector. Okay, and we'll just give it the symbol 0 here. Okay, so this symbol 0 here, this is going to represent the 0 vector. Okay, now this is where this is going to get incredibly confusing because we're also going to have an additive identity in the field, capital F, which we're also going to call 0. Okay, but it's going to be a different element in a different number system. Okay, so we have 0 representing the additive identity in the field and 0 representing the 0 vector in the vector space, but I hope it will all be clear even though there is that ambiguity. Okay, so what we're now going to consider is we're going to use part 2 of distributivity, the second distributive law here, to actually understand what the additive identity in the field multiplied by any vector is actually going to do. So we're going to be looking now at the column dedicated to the element 0, the row dedicated to the element 0 in the field. So here we have the additive identity in the field, and we're going to be able to scalar multiply all of the vectors in the vector space by 0, and we'd like to know what's that going to do. Well, the intuitive answer is that it's going to send all vectors onto the 0 vector, the additive identity in the vector space. Okay, but we need to prove that. And we can use this second distributivity law to prove that. Okay, so what we're going to quite simply do is we're going to say, okay, let C2 equal 0. Let C2 equal the additive identity in our field. Then what we'll get is that C1 plus 0 times any vector from our vector space must equal C1 times that vector plus 0 times that vector, just by this distributivity law, which we are insisting is going to be true in our vector space for the scalar multiplication composition. Okay, now what we can do is just analyse this a bit more, because C1 plus 0 in the field, whenever you add any element of the field to the additive identity in the field, just by definition that's going to give you the same element back again. So this side is going to become C1 times V. Okay, now what we have is that this vector C1 times V is equal to C1 times V, another vector, plus 0 times V, okay, where this is addition in our vector space addition law. Okay, but because our vector space addition law is an abelian group, it's going to have additive inverses, so we can now just compose on either side with the additive inverse of C1 times V. So I'll just have plus negative C1 times V. Okay, the additive inverse of C1 times V in my vector space. Okay, so on this side then, I will get the 0 vector, the additive identity in my vector space. On this side, the C1 times V will vanish, and I'll just be left with 0 times V. Okay, so what that tells me is that 0, the additive identity in my field, and I'll just colour this in to make it clear, this is 0 from the field. This is the additive identity from the field, whereas this 0 here, this is 0 from the vector space V. Okay, so what this is saying is that if I scalar multiply 0 by any vector in my vector space, I get the 0 vector back again, which is the intuitive answer. So this entire row dedicated to the additive identity of the field will just be full of the 0 vector as all of the answers, basically. Okay, so that then now completes the definition of what a vector space actually is. In the next video, what we'll do is we'll actually look at examples of how to construct these things. Okay, so we'll take an abstract field, capital F, and we'll aim to actually construct a vector space V over that field F.